So in this video, I'm going over the Chapter 5 review. It tells me that for the first 3 questions, we'll be referring to this two-way table. And it says a group of 125 truck owners were asked what brand of truck they own and whether or not the truck has 4-wheel drive. The results are summarized in the two-way table below. And then based on that, answer the following questions. So the first thing I want to do with my two-way table is I want to add up my columns and rows. So I am going to figure out how many people own a Ford in the survey. There are 45. Then I'm going to figure out how many people own a Chevy. There are 50. And then I'm going to do the same thing for Dodge. There's 30. Then I want to total all the way down. So how many yeses there are? 28 plus 32 plus 20 is 80 yeses. And then I want to add my no's down. 17 plus 18 plus 10 gets me 45. And then 80 plus 45 or 45 plus 30 plus 50 should both give me 125. So now that I know I have a total of 125 people, one is, what's the probability that the person owns a Dodge or has a 4-wheel drive? So the total number of people with Dodges are 30 out of 125. 4-wheel drive is 80. And then I have people who are being double counted. So people with Dodges and 4-wheel drive are 20 out of 80. Or 20 out of 125. Everything here is 125. So then I want to add these fractions together. 30 plus 80 is 110, minus 20 is 90, and I'm still over 125. So my answer for number 1 is D. So this is where I add the two probabilities together and subtract the overlap, because you can be both at the same time. Okay. My next one says, what is the probability that the person owns a Chevy given that the truck has 4-wheel drive? So my numerator is going to be owning a Chevy and 4-wheel drive. So that is going to be 32. And then it's out of how many total 4-wheel drives there are. So there are 80 4-wheel drives. So this answer here is B. Whatever is after my given goes on the denominator of the fraction. And then whatever it says first is what I want to find given that condition. So it has to be both of those for the numerator. Number 3 says, which of the following is true about the events? Owner has a Chevy and owner's truck has 4-wheel drive. So this one is asking me to decide if they're mutually exclusive and independent. In order to check for this, I need to see the ratio for these. So the first ratio I want to check is being a Chevy with 4-wheel drive. This is 32 out of 80, which if I simplify on my calculator, 32 divided by 80 gets me 0.4. Then I want to check being a Chevy in general out of the total cars, so 50 out of 125, which again gives me 0.4. So this means they are independent, but they are not mutually exclusive because you can be both at the same time. So not mutually exclusive and independent is C. Okay. So number 4 says a spinner has 3 equally sized regions, blue, red, and green. Johnny spins the spinner 3 times and gets 3 blues in a row. If he spins the spinner 279 more times, how many more blues is he most likely to get? So this one is the law of large numbers. So how many blues he has already gotten does not matter. What I want to do is he has a 1/3 chance of getting blue, and there are 297 more spins. So I want to take 1/3 and multiply it by 297, which gives me 99. So he is likely to get 99 more blues. This isn't saying for sure he's going to get 99 more blues. It's just likely that he will get 99 because he has a 1/3 chance. Sorry for printing single-sided. I didn't catch it until after all of these had printed. So number 5 and 6 refer to this following setting. Wilt is a fine basketball player, but his free throw shooting could use some work. For the past 3 seasons, he's made only 56% of free throws. His coach sends him to a summer clinic to work on a shot, and when he returns, his coach has him step to the free throw line and take 50 shots. He makes 34 shots. Is this result convincing evidence that Wilt's free throw shooting has improved? We want to perform a simulation to estimate the probability that 56% free throw shooter would make 34 or more in a sample of 50 shots. So what I want to do here is I'm going to read through each of these ways to perform a simulation and then decide whether or not, or decide which one is the correct method. And as I'm reading, I'm going to decide whether or not they are the correct choice. So A is let integers from 1 to 34 represent making a free throw, and 35 to 50 represent missing a free throw. So this is giving him a 34 out of 50 chance, which he is currently at a 56%. So 34 out of 50 is 68%. This one's not my answer. B says let integers 1 through 34 and 35 to 50. Again, this is a 34 out of 50 chance. So not right. C says let integers from 1 to 56 represent making a free throw, and 57 to 100. So he is making 56 out of 100, so we'll keep reading. It says generate 50 random integers from 1 to 100, count the number of made free throws, and then repeat this process many times. Sounds good. I'll hold on to it and read D. D says let integers 1 through 56, making a free throw, and then 57 to 100 missing a free throw. Generate 50 random integers with no repeats allowed. I'm allowed to repeat. If I did this multiple times, I might happen to make the same number of shots multiple times. So this one's not right. And, oops, that should have been an X on D. And then C was correct. I just needed to make sure it was the best choice out of C and D. So, number 6 says the dot plot displays the number of made shots in 100 simulated sets of 50 free throws by somebody with the probability of 0.56 of making a free throw. So, which of the following is an appropriate statement about Wilt's free throw shooting based on this dot plot? So, in the context we had up above, it was talking about him specifically making 34 or more out of the 50 shots. So I have 3 out of 100, which is 0.03 as a decimal. And then it says, if Wilt were still only a 56% shooter, his probability that he would make at least 34 of his shots is only about 0.03. B is if he was only a 56% shooter, his probability would be 0.97. That one's not right. If Wilt was now shooting better than 56%, his probability would be 0.3. We are focusing only on him still being a 56% shooter, so that's not true. And then the rest of them are not the percents I got. So A is my correct answer here. Moving on. Number 7 says the partially complete table shows the distribution of scores on the AP Statistics exam for our class of students. So it gives me this, and then it has a question mark for number 3. Before I even get started on this problem, I want to find that missing value. I know these need to add up to 1, so what I'm going to do is I'm going to do 1 minus all of my known probabilities. So minus 0.10, 0.20, 0.25, and then 0.15. And then I will type this on the calculator. Oops, I did not mean to type that twice. Which gets me 0.3. So then, this one says to select a student from the class. If the student scored a score of 3 or higher on the AP Statistics exam, what is the probability that the student scored a 5? So scoring a 5 is 0.15, and I'm only looking at students who scored above a 3. So on my denominator, I'm adding the probabilities for 3, 4, and 5s together. If I want to type this straight into my calculator, I want to make sure my denominator is all in parentheses. So then I would type this in. I have 0.15 divided by 0.3 plus 0.25 plus 0.15, which gives me 0.214, which is choice B. Number 8 says in a class there are 18 girls and 14 boys. If the teacher selects 2 students at random to attend a party with the principal, what is the probability that the 2 students are the same sex? So first thing I want to figure out is the probability of getting 2 girls. I have 18 out of 32 girls because I have 32 total students. For my first choice, I want to make sure I get a girl on the second choice if I get them on the first one. So I have 17 over 31. Or I could get 2 boys in a row. So then I could also do, oops, there was not 18 boys. There are 14 boys. Out of 32 times 13 out of 31 the second chance, because I have 1 less boy to choose from and 1 less total student. Then what I'm going to do is, once I find these 2 probabilities, I want to add them together. So I'll figure them out first. 18 divided by 32 plus 17 divided by 31. Oops, those should have been multiplied. No. So I'll write it out to 3 decimal places. I have 0.308 for that one, and then I have 14 out of 32 times 13 out of 31, which gets me 0.183. So if I add these 2 together, I get 0.491, which, due to rounding differences, is A. Number 9 says, suppose that a student is randomly selected from a large high school. The probability that the student is a senior is 0.22. The probability that the student has a driver's license is 0.3. If the probability that the student is a senior or has a driver's license is 0.36, what is the probability that the student is a senior and has a driver's license? So I know that I'm going to use S for senior and D for driver's license. Okay, so the probability of S or D is found by taking the probability of S, adding the probability of D, and then subtracting the probability of S and D. So I want to replace those probabilities with what I know. So I know the OR probability is 0.36. I know my senior probability is 0.22. My driver's license probability is 0.30. And then the AND is what I'm looking for. So then I kind of solve this just like a normal algebra equation. I want to combine those 2 probabilities on the right side. 0.22 plus 0.30 is, I could have done that in my head, 0.52. Oops, this is S and D, not A and D. And then I want to subtract the 0.52 on both sides. Which gets me negative 0.16 equals negative the probability S and D. So if I divide both sides by negative 1, this gets me 0.16. So my answer here is E. Number 10 says the security system in our house has 2 units that set off an alarm when motion is detected. Neither one is entirely reliable, but one or both always go off when motion is anywhere in the house. Suppose that for motion in a certain location, the probability that A goes off and detector B does not go off is 0.25, and the probability that detector A does not go off is 0.35. what is the probability that detector B goes off is, what is the probability that detector B goes off? So, one way to think about this is I can go ahead and draw a Venn diagram. I have two motion detectors, A and B. I know that A going off, but B not going off is 0.25, and that A not going off and B going off is 0.35. Then I know, because these are probabilities, they have to add to 1, so I can find my missing probability. 1 minus 0.25 minus 0.35 gets me 0.4. And I just want the probability that detector B is going to go off. So in order to figure this out, I want to add everything inside my B circle. So over here, that is 0.4 plus 0.35, which gives me 0.75. So my answer here is B. This next one gives me a two-way table, and it is summarizing on whether the students at a certain high school regularly eat in their cafeteria by their grade level, and then I have the totals on this one. If you chose a student at random, what is the probability that the student regularly eats in the cafeteria and is not a 10th grader? So I could just add everyone who is yes except for a 10th grader. So I have 130, 122, and 68. And I'm just looking at all of my students, so it's out of 805. So if I type this in the calculator, I would want my numerator in parentheses. Oops, I forgot to divide. Which gives me 0.398. Okay. B wants me to choose a student randomly who is just a 10th grader, so who eats in the cafeteria. So there are 175 10th graders who eat in the cafeteria, and I am specifically looking at ones who regularly eat in the cafeteria. So there are 495 students who regularly eat in there. I will divide 175 by 495, which gets me 0.354. C says, are the events 10th grader and eats regularly in the cafeteria independent? Justify my answer. So what I want to first figure out is how many 10th graders I have. I have 209 over 495. So if I find, where did I get that? I don't know where I got the 495 from. I wanted it out of total number of students. There are 209 10th graders out of 805 total students. Which gets me 0.260. And then I want to see how many 10th graders eat in the cafeteria. So this is 175 over 209. Oh, no, not 209. These are 10th graders who eat in the cafeteria compared to total people who eat in the cafeteria. So the 495, the one I just found on part B, which is 0.354. My answer here is no, because the probabilities are not the same. What was the first one? Probability of 10th grader. Is not the same. as the probability of a 10th grader and then regularly eats in the cafeteria. Okay. Number 12 says 3 machines A, B, and C are used to produce a large quantity of identical parts at a factory. Machine A produces 60% of the parts. B and C produce 30 and 10% respectively. Historical records indicate that 10% of the parts are produced by 10% of the parts produced by machine A are defective, compared with 30% for B and 40% for C. So suppose we randomly select a part produced at the factory, find the probability that the part is defective. I am going to start off by drawing a tree diagram. So I have 3 different parts. I have A, B, and C. And then I want to write their probabilities that they'll be made on each of these branches. So I have 0.60 for A, 0.30 for B, 0.10 for C. Then I have my defective for A, and my OK. And those are 0.10 that it's defective, 0.90 that it's okay. To figure out the OK, I just took 10% and subtracted from 100. Same thing for B. So I have my defectives and my OKs. For B, it is 0.30 defective, 0.70 OK. And then C's, I want to go ahead .40 defective, 0.60 okay. Then I need to figure out the probabilities for each of these things. So I take the two percents as decimals and multiply them together. So I have 0.6 times 0.10, which gives me 0.06. Then I have 0.6 times 0.9 gives me 0.54. 0.3 times 0.3 gives me 0.09. 0.3 times 0.70 gives me 0.21. And 0.10 times 0.40 gives me 0.04. And 0.10 times 0.60 gives me 0.06. I can check to make sure all of these add up to 100 because probability should be out of 1. So I'm going to do that just to double check to make sure I've done my math right. Which gets me 1, so I've done my math right. This question was asking for defective parts, so that was the 0.06, the 0.09, and the 0.04. So I want to go ahead and add those together. Which gives me 0.19. Okay, B says if the part is inspected and found to be defective, what is the probability it was produced by machine B? So, being defective in part of machine B was 0.09. And I know that it was defective, so I want to use my 0.19 that I got from part A, because that is the probability that it's defective in the first place. And then I just divide these two, so 0.09 divided by 0.19 gives me 0.474. So, number 13 says at Dicey Dave's Diner, the dinner buffet usually costs $12.99. Once a month, Dave sponsors Lucky Buffet Night. On that night, each patron can either pay the usual price or roll 2 fair 6-sided dice and a number of dollars equal to the products of the number equal to the product of the numbers shown on the two faces. The table shows the sample space of this chance process. A says a customer decides to play Dave's Lucky Buffet game. Find the probability that the customer will pay less than the usual cost of the buffet. So first thing I want to figure out is how many chances there are to pay less than the buffet. So I need to pay less than $12.99. There are these 6. These 6 are all less than $12.99. Then I have these 4, these 3, these 2, and these 2. So I want to add up how many total things I've just highlighted. I had 6, 12, 16, 19, 21, 23. So there are 23 out of 36 total chances because it's a 6 by 6 grid. So then I just want to divide. Oops. 23 divided by 36. There's a 0.639. So there is a 0.639 probability that the customer will pay less than the usual cost of the buffet. So B says a group of 4 friends comes to Dicey Dave's Diner to play the Lucky Buffet game. Find the probability that all 4 of these friends end up paying less than the actual cost of the buffet. Because there's 4 friends and they all have the same chance, I'm going to do 0.639 raised to the 4th power. Oops, helps if I type it in, right? So this gets me 0.167. So there is a 0.167 per, there is a 0.167 probability that all 4 friends will pay less than the usual cost. C wants me to find the probability that at least one of the 4 friends ends up paying more than the usual cost of the buffet. So because I'm looking for 1 friend specifically, what I'm going to do is I can either do 1 minus 0.639 to the 4th power, or I know that 0.639 to the 4th power is 0.167, so I could just subtract that, which gives me 0.833. So there is a 0.833 probability that at least one of the 4 friends ends up paying more. Moving on to my last question. It says, based on previous records, 17% of the vehicles passing through a toll booth have out-of-state plates. A bored toll booth worker decides to pass the time by counting how many vehicles pass through until he sees 2 out-of-state plates. We would like to perform a simulation to estimate the average number of vehicles it takes to find 2 with out-of-state plates. A, describe how you would use a table of random digits to perform the simulation. So first I need to assign my values. So I'm going to write to carry out the simulation. With random digits. I'm going to let 00 through 16 be cars with out-of-state plates. This is 17 total cars because 0 counts as a number. And then 17 to 99 are going to be the other cars. And then I want to move left to right on the rows. Until I have two numbers between 00 and 16. And it's it's okay if I have repeats. Because that's just like in this hypothetical situation, it's like having 2 California plates. That's fine. And then record how many 2-digit numbers you had to read in order to get 2. And then repeat many times. Oops, I want to say numbers. Okay, so then B wants me to perform 3 trials using the random digits here, marked directly on above so someone can follow what I did. So I'm going to break it up into 2 digits. 41 is not an out-of-state, 5 is, 9 is. So this one, it took 3 cars, so in the first trial. And I'm going to do it again for the second trial. So 51, not between 0 and 16. 11, between. 58, not. 44, not. 69, not. 94, not. 86, not. 85, not. 79, not. 67, not. 5, yes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So, wait, let me count again. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, it took 11. And then I want to do it a third time. So then I have 84, too high. 17, too high. 70, too high. 67, too high. 57, too high. 17, too high. 61, too high. 31, too high. 55, too high. 82, too high. 51, too high. 50, too high. 68, too high. 14. And then 35 is too high. So I did not get 2 cars. Wait, let me double check. Yeah. Oh, just kidding, I'm stupid. I did the first one right, but I should have continued my numbers after that first list. So I'm just going to rename this so you can see where I started my trials. There you go. So as long as I clearly label what my trials were, I am good.